Hello everyone, welcome back to our channel. In today's tutorial, we are going to learn about an important technique in RAG called query decomposition with Fusion. This is a technique that greatly improves our final response quality actually. If you have followed our earlier tutorials, you must have understood the basic vanilla RAG pipeline. So the basic vanilla RAG pipeline works like this actually. We take our basic query and we embed it into some numerical vector form, and then using that embedded vector we retrieve top k matching chunks using a retriever, and then whatever the retrieved chunks we get, we will combine them with the query, and we will send that entire thing to LLM, and the LLM returns the final answer. So this is the basic vanilla RAG workflow. It works well for most of the cases actually, but it has one big weakness. Sometimes the questions are multi-part or compound questions. For example, here, if you look at here, if you take any question like this, how are boundary conditions enforced in pins and how are PD residuals computed? If you take a question like this, if you pass this whole thing as a single embedding, the retriever sometimes may only stick onto one part of this question actually. It sometimes may stick to boundary conditions or pins or PD residuals, or sometimes it may stick to boundary conditions and pins, and sometimes it may exclude this PD residuals altogether because of so many reasons, hallucinations or inappropriate context, or sometimes the token restrictions. For various reasons, if LLM excludes any particular part of this question, then we won't get reliable response for this entire question actually. This is one of the fundamental problem with vanilla RAG, and this is where query decomposition with Fusion comes in. The basic idea of this query decomposition fusion process is quite simple actually. Whenever we get this query, so we generate certain number of subqueries for this original query. For example, here if you take this original question, how are the boundary conditions enforced in pins and how are PD residuals computed? So this is our original query, and for this original query we generate these many number of subqueries. For example, here we generated some subqueries like enforcement methods for boundary conditions, loss functions, computation of PD residuals, and the role of automatic differentiation in residual calculation actually. So these are all some four subqueries. They are related to this original question, but these are not directly in the original question. Okay. For each subquery, we call this subquery loosely as a facet actually, because each facet deals with one aspect of this query. So that's why we are calling it a facet. So for each subquery, and we embed this each subquery and retrieve chunks for each facet actually. So here, for example, if we have four subqueries, we get, for example, if we take a k is equals to 5, we get a total of 4 into 5 is equals to 20 chunks. Okay, and we won't use this 20 chunks as context to LLM actually. We use a certain process called fusion, and within that we use a methodology called reciprocal rank fusion. In this, we extract some chunks, maybe 3 or 4, or sometimes if you want 5 top most relevant chunks from this 20. So we extract some 3 or 4 or 5 chunks from this 20, and we build a context using these chunks, and we couple that context with query, and we send this query plus context to LLM, and we generate this final answer. So this is the overall method that was involved in this query decomposition and fusion process actually. We will discuss this method in detail now. Let's get started. Let's now implement this step by step. So here I'm using the corpus that we build in our earlier tutorial on agentic RAG. This is one of our earlier tutorials. We build a complete agentic RAG from scratch here actually. In this tutorial, we discussed in detail about how to generate these chunks actually. So here we took the original PDFs, and we discussed the entire process of generating the chunks using this embedding model, all mini LM L6v2. So if you want, you just please go through this tutorial, you will get the complete idea. So for now in this tutorial, we are going to use the same index, the FAISS index that we generated in this phase. We are going to use the same and work on our query decomposition and fusion process actually. So here I'm loading our main chunks and this FAISS index. As I said, they are here. If you go to our original directory, you will see this data and raw PDFs. So here you will see our original PDFs, and another directory you will see called a vector store. Within that you see this pickle and FAISS file. So we are just loading these two pickle and FAISS files into our current notebook, that is phase 2 v2 facet RAG. So we have got a total of 227 chunks and metadata for all these 227 chunks, and in FAISS index we have a total of 227 embeddings actually. So if you look at here, 227 here, 227 here, 227 here. So we have got a complete data. There are no missing details actually. And now we are going to use this data for implementing our query decomposition process actually. So here I'm implementing some basic functions actually. So here I'm going to use OpenRouter for this work. We are using this for quite some time. For all our earlier tutorials, you will see this OpenRouter in our earlier tutorials as well. So here we are going to use this DeepSeek chart v30324 model, and this is our basic call LLM function. We call this LLM function multiple times in our subsequent logic actually. So here I have written some parsing function. We'll see it shortly why it is used. And here is our basic decompose query function actually. So what it takes is, if you look at here, decompose query, it takes a string and a number called minimum facets and the maximum facets that we are expecting it to generate. I have set minimum facets as 3, maximum facets as 5. So, and we have given this system prompt like this: return only a JSON array, no code fences with minimum facets, maximum facets. It means with minimum of some 3 to 5 facets items. Okay, each item must be a short subquery that stays on the same topic as the question. So sometimes what happens, the subqueries will be generated completely in a random way. For example, if you take this original query, how are boundary conditions enforced in pins? If you leave this entire pin and if you only take this boundary conditions as a separate entity, and if you generate a subqueries based on that, then it won't match actually. It won't be relevant, because boundary conditions in general, they can mean many things, but we are expecting what does it mean in pins. Okay, so that's why we are restricting the LLM to stay on the same topic as the question and reuse keywords from the question. Do not invent new domains. No pros, no objects, no keys, just a JSON list of strings. So this is what we are giving as a system instruction. And then this is our user instruction actually. Split the question into focused subqueries that cover different angles, definition, scope. We are giving some instructions here, and then we are giving an example format in which we are expecting. So this is an example, it won't use it as it is. And this is our question. So when we send this question to this, it calls this LLM, and here we are doing some parsing. Why it does what it does is, sometimes what happens is this LLM not only just returns the text entities, it returns some keys and all. So here what we are doing is, we are just extracting the text from it, that's it. And here we are doing another check actually. What happens is, sometimes the LLM won't return, we asked for 3 to 5 facets, right? Sometimes it just give one facet and stays away. So that's what we are doing, it another cross check here. So if it is 1 or less than minimum facets, so we are calling the LLM again to generate the more number of facets. So we are expecting some 3 to 5 facets. So that is the condition that we are putting it here actually. So if it generated anything less than the minimum facet number, so it generates more number of facets here. And then we are extracting only the questions, the facets from here, and we will try to remove all the keys, if at all, if any exists on the JSON file, and we are sending the facets from here, from this function actually. So that's what these call LLM and parse list functions does actually. And here is our basic query. Here is what we are giving it: how are boundary conditions enforced in pins and how are residuals computed for this query. So these are all the sub questions that were developed. So here, what are common types of boundary conditions? This is one facet, and this is one facet that LLM generated. This is another facet, this is another facet, this is another facet. And one more thing is, whenever this code runs completely, every time you will see a new facets, but more or less they are somewhere like this actually, because we have given system instructions and user instructions very strictly, such that it follows some restrictions and guardrails here, and it will try to generate the same facets in different ways actually. And here, after we generate the facets, here we are doing this step called per-facet retrieval. We are not retrieving chunks for the entire query. We are going to retrieve chunks for each facet here actually. So total, how many facets we have? 1, 2, 3, 4, 5. A total of 5 facets we have, and we expect, we are giving some top 3 matching chunks, but here we are giving a k as 5. So total we expect 5 chunks for each of it, and this is our retrieval process. And once we pass our facets through this process, we get to see all the results here. So top results and results I kept it same. So what we are going to print all the retrieved chunks from this retrieval process. If you want to see a less number of chunks to save this printing space, so you can restrict the printing limited to 3 or 2, whatever you want. But here I am printing all the chunks retrieved actually. So maximum of 5 chunks has been retrieved, and this is the chunk details for this particular facet. Okay, so for this particular facet you have got 5 chunks here, and based on the score from top to least, we have assigned some ranks actually. So this score is the similarity score. For the highest similarity score, we have got rank 1. For the lowest similarity score, we have got rank 5 here, because we have taken only 5 chunks, right? So it's got 1 to 5 ranking. Okay, and these are your chunk numbers. The document is same, but the chunk number within the document are different actually. So chunk 118 got rank 1, chunk 119 got rank 5. Similarly, this is for second facet. Similarly, this is for third facet, fourth and fifth one. So right now we have 1, 2, 3, 4, 5. 5 fives are 25 chunks we have. Next, we have to do a process called reciprocal rank fusion. So using this reciprocal rank fusion, so we are going to extract some top n chunks. So in our tutorial we have considered top n as 3. So it means from these 25 chunks we have to finalize 3 chunks. How are we going to do that? And that process we do using this reciprocal rank fusion. So what it does loosely is, we have got some numbers we will assign to this ranks actually. Rank 1, so here k is a smoothing constant, so by default we are keeping it as 60, and this is our reciprocal rank function. It is 1 by k plus rank. So k is your 60, it's always constant, and rank is your document rank. So what happens is, these are your rank always stays same, right? So for 1 it is constant is 1 by 61. For rank 2 it is 1 by 62, that is 1 by 60 plus 2. For rank 3 1 by 63. For rank 4 1 by 64. For rank 5 1 by 65. So these are some factors that we are assigning for rank 1, rank 2, rank 3, rank 4, rank 5. Okay, for example, imagine we have these 3 chunks actually. This is chunk 122, chunk 118 and chunk 137. Likewise, we can have any number of chunks. Here we have these many chunks, right? 118, 122. So likewise, let's take just 3 chunks of all these things actually. These 3 chunks I have randomly chosen. There's no special meaning for it. If not, you can use any number, and I have chosen just for explanation purpose. Okay, for example, if you take chunk 122, and in this facet 1, chunk 122 appeared at rank 1, and chunk 137 appeared in rank 4. In facet 2, chunk 118 appeared in rank 1, and chunk 137 appeared in rank 5. And in facet 3, chunk 122 appeared in rank 3, and 118 appeared in rank 2 position actually. So likewise in F4, in F5. So that this chunk 122 in facet 1 we assign this score. Okay, and similarly in facet 3 it got this score, and in facet 4 it got this score depending upon its rank in each facet. So and in facet 2 and facet 5 this particular chunk 122 is not available. So we combine these three and we assign the total score for this chunk 122. So chunk 122 got this score. Similarly, chunk 118, it appeared in only F2 and F3, and it did not appear in F1, F4 and F5. So in F2, it appeared in rank 1, and in F3, it appeared in rank 2. So we sum these two and we assign the total score to chunk 118, this one actually. Similarly, chunk 137, it appeared in facet 1, facet 2 and facet 5 and did not appeared in facet 3 and facet 4. So we assign the numbers corresponding to its rank in each facet. In facet 1 it got 4th rank, in facet 2 it got 5th rank, in facet 5 it got third rank. We sum all these three and we assign the total score like this. Okay, and now we compare these three. Okay, 0.048, 0.03, 0.046 of these, chunk 122 got the highest score as 0.048 and chunk 137 got the second score 0.04 and chunk 118 got 0.03. So this is our list. So likewise we arrange these chunks based on the scores it get. Likewise, we evaluate the total scores for all these chunks, and once we have got the total score, we sort them in the descending order. So the one with the highest score stays at the top, and the one with the least score stays in the bottom. And for understanding purpose, here we are normalizing the scores with respect to the maximum. Maximum means the first one which got the highest score will get 1 always in this normalization process, and the remaining ones will get appropriate scores with respect to the maximum score. This is what we are doing here in normalization process. And once we get these scores depending upon our requirement, this particular tutorial we have just taking top 3 chunks actually. So if you want, you can take top 4 chunks or top 5 chunks, no problem. So it means this is your total chunks, and the first one got 1 score, second 122 got this much, and this is your fused chunk order actually. So the first one is chunk 118, and if you take top 3 as priority, and these are the 3 chunks that you are going to consider, that is 118, 122 and 134. If you take top 5 as your priority, then you are going to consider these 5 as your priority actually. So for now we are just limiting ourselves to top 3 to build the context, and here we are building the context. Context building is simple actually. So what we are going to do is we will be taking the text in each of this chunk, and we will append one by one here like this. So each chunk got this kind of text, right? So for example, we will place this one as first, and for example, if this is the second, we will place this one in the second, and if this is the third, and we will place this one in the third. So we will concatenate, we will stack all these three texts together. Yeah. So loosely you will get 3 paragraphs actually, and those 3 paragraphs combinedly is called our context. And we will combine this entire context here with this query. So we are sending both the query and the context. Context means the 3 paragraphs that we just retrieved from the fused process, and we will combine this query and context here actually. So here we are giving this system message like this: you are a helpful tutor, use the provided context to answer clearly, format your entire response in markdown with appropriate headings, bullet points, and use this single dollars for inline equations and double dollars for block equations. And we are just sending this query with context and no other extra parts in this user query actually, just the question and the context. And we will be sending this system prompt and this user prompt together to the LLM to retrieve the final answer, and this is your final answer actually. Because of this fusion process, you got this much detailed answer. If you use vanilla RAG, you won't get your answer in detail for sure. Okay, and here I am printing this entire answer. We have got in markdown, right? Here I am just rendering that into proper visually good format. So this is your thing actually. So here the first question is enforcing boundary conditions. So here this is how we enforce boundary conditions. It is saying that, and w1 w2 is equals to 1. It's talking about weights here, and this is how we calculate this LBC, and here it is saying something about boundary conditions, and here it is telling something about the PDE residuals here how we evaluate this LPD, and this is how we compute derivative computation. So this we did not ask, but it came through facets. Okay, let's try one more with another query. Here we have another query here. So the query is, how is Monte Carlo method used for fast computation of second derivatives? So let's run this. So this question I have taken from this PDF, and this is a PDF we included in our corpus actually. So I asked the same question, a Monte Carlo method for fast computation of second derivatives. So it is what written here. I just asked it straightly here, how is Monte Carlo method used for fast computation of second derivatives? I'm expecting something from this particular doc actually. I'm not expecting anything different from its LLM's knowledge. I'm expecting a very specific response that was taken from this particular chunk. Okay, and when you run it, it will take a while for it, and finally you will see some chunks generated. So these are the facets that were generated. So definition of Monte Carlo methods for derivative estimation, Monte Carlo algorithms for approximating second derivative, variance reduction techniques, error analysis of Monte Carlo second derivative estimators, and computational complexity of Monte Carlo second derivative. These are some facets that were generated for this particular question, and we retrieved some chunks for each facet, and then we did the same fusion ranking process, and then we took the top three matching chunks, and then we pass the original query with the generated three context paragraphs with this query, and we send them combined to the LLM, and we got this final answer. If you look at the final answer in this rendered form, we have got the second derivative term can be approximated as this particular equation. If you look at your original paper, yes, it is written like this, and this is can be approximated like this actually. And then here in the same paragraph, you have got some four steps, the modified algorithm using the Monte Carlo approximation for second derivative. So here they have given some algorithm to approximate the second derivatives, and it was able to extract this algorithm also has well a random sampling, gradient approximation, parameter update, and iterate until convergence. So we have got all the four algorithm steps, and then it gives some trade-offs and applications actually. So you got the response from the PDFs. So this is how we do this query decomposition with Fusion. So with vanilla RAG, you have one query, you will have one retrieval, and of which some parts of the question may miss in your final answer. And here is your current query decomposition and fusion workflow. So here we break the query into several number of facets, and we retrieve chunks for each facet, and we fuse them fairly using this process called Reciprocal Rank Fusion, and we generate some top matching chunks, and we build a context out of it, and we combine that with the original question, and we will send it to the LLM. And this particular changes, the small changes that we are doing makes a really big difference, especially for technical or compound questions actually. So that's it. In this entire tutorial, we have built the whole pipeline from scratch. So the query decomposition explained, per-facet retrieval explained, reciprocal rank fusion explained, and context building process is explained, and the final answer generation is also shown actually. So that's it for this tutorial. You have found this tutorial useful. Please like the video, subscribe to our channel, and drop your questions or suggestions in the comments. Thanks for watching, and as always, happy learning.